Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, we'll be looking at how to build a convolutional neural network model for image classification. Even before I proceed to demonstrate how to build a convolutional neural network model using Jupyter Notebook, may I request you to subscribe to my channel, also like and share my videos. Let me begin by introducing you to the folder that I have created. I have a folder containing the images of 15 cats and 15 dogs. The goal here is to build an AI model to classify cats and dogs. To build an AI model to classify cats and dogs, we will use the deep learning model and specifically the convolutional neural networks. We will use the Keras library. Now, one question that you might ask is, what exactly is Keras? Keras is a high-level API for deep learning and makes it easy to build and train the artificial neural network. Let me quickly show you the data set that I have. As you can see here, in the desktop, I've got a folder which is called as pets. Here, I've created two subfolders. In the first subfolder, I have 15 images of cats, and in the second subfolder, I have 15 images of dogs. Let me quickly click on the first subfolder. You can see here, these are some of the images of cats that I have. I have put it in one folder. Similarly, when I scroll back, you can see this is the second folder that I have. This is a folder which is called as the dogs subfolder. Let me click on this particular subfolder. As you can see here, there are 15 images of dogs that I have lined up. This is the first image. This is the second image, third, fourth, fifth, so on and so forth. The goal here is to train a deep learning model so that it can classify dogs and cats. Most of these images I have downloaded by going to Google Images. I've also downloaded a lot of images from a website which is called as www.pixels.com. So credit must be given where it is due. So full marks to these people for making these images available. Let me now go on to Jupyter Notebook, wherein I have written the code to classify cats and dogs. As you can see here, this is the Jupyter Notebook, which I will be using to build the CNN model. Just to give you a high-level perspective about CNN or Convolutional Neural Network is a type of neural network. Broadly speaking, when we talk about neural network, there are two different schools of thought. The first school of thought is what is called as RNN or recurrent neural network, which is mainly used for textual classification, sentiment analysis, so on and so forth. On the other hand, you have the second type of neural network, which is called as convolutional neural network. This kind of neural network is mainly used for image classification. Convolutional neural network is widely regarded as a gold standard for image classification. As you can see here, in the first line of code, what am I doing? I'm importing the necessary libraries. One of the first libraries that I would like to import is the TensorFlow. After importing TensorFlow, I'd like to also import certain functions like convolutional 2D, max pooling 2D, flatten and dense. Further, I will be importing the sequential function from tensorflow.keras.models. Lastly, from tensorflow.keras.preprocessing.image, we will be importing what is called as the image data generator. So in the first line of code, all that I'm doing is I'm importing the necessary libraries. Let me now go to the second line of code. As you can see here, in the second line of code, all that I'm doing is I am setting the path to the folder containing the images. The folder is called as the pets folder, and this is present in the desktop. So I have specified the path of the folder, which consists of the two subfolders. Let's now talk about the third line of code. Let me execute the second line of code. I'll now move on to the third line of code. In the third line of code, what we are doing is we are creating an instance of the image data generator class, and we will be specifying the parameters here. One thing to remember is Keras image data generator. Why do we need Keras image data generator? The answer is very simple. Keras image data generator is used for getting the input of the original data, and further it makes the transformation of this data on a random basis and gives the output resultant containing only the data that is newly transformed. Note, in this particular code, we are using a very important parameter which is called as rescale. Now, you might ask me, what exactly does the rescale parameter do? Simply put, the rescale parameter scales the pixel values to a value between 0 and 1. I repeat, the rescale parameter scales the pixel value to a value between 0 and 1. Further, you have the parameter which is called as validation split. What is this validation split? Validation split splits the data into training and testing. As you can see here, I'm going to use 20% of the images for validation. The balance 80% will be used for training the deep learning model. Let's now move on to the next code. What are we doing here? As you can see here, in this piece of code, I'm going to create two generators for the training and the validation sets. I repeat, in step 4, I will be creating two generators for the training and validation sets. This is the first generator that I'll be creating. This is called as train_generator. And this is the second generator that I'll be creating, which is called as the validation generator. You have a very, very important function, which is called as flow from directory. What does this datagen.flow from directory do? Let me answer this question. The flow from directory method loads the images from the folder and resizes them to 150 by 150 pixels. You can see here, this is what we want. We want the flow from directory method to load the images from the folder and resize them to 150 by 150 pixels. Further, you see a very important parameter here, which is called as batch size. What exactly do we mean by the batch size? Simply put, the batch size parameter specifies the number of images to process at a time. Last but not the least, you have an option which is called as class mode. We are specifying the value here as binary. What is this class mode? Class mode is a parameter which specifies that we have a binary classification problem. Remember, we are interested in training the algorithm to recognize cats and differentiate cats from dogs. If we go ahead and execute this particular command, you can see here, it says found 24 images belonging to 2 classes. It also says found 6 images belonging to 2 classes. So 24 images belonging to 2 classes, namely cats and dogs, will be used for training. And out of the 30 images, the remaining 6 images will be used for testing the algorithm. In the next step, what we will be doing is we will be defining the model architecture. I repeat, in the next step, what we will be doing is we will be defining the model architecture. What exactly are we doing in this in this line? What we are doing is to define the model architecture. Let me give you a 10,000 feet perspective as to what we are doing in this code. Then I'll explain step by step what each line means. We are using a series of convolutional and pooling layers. As you can see here, this is the convolutional layers, this is the convolutional layer, and this is followed by the pooling layer. Not just one convolutional layer and pooling layer, we are using multiple convolutional layer followed by the pooling layer. You can see here, these are the different convolutional layers which are followed by the pooling layers. Why are we doing this? We are using a series of convolutional and pooling layers to extract features from the images. The final layers are fully connected layers that perform the classification. Let me quickly show you the final layers here. You can see here, this is the final layer which performs the task of classification. The output layers has a sigmoid activation function. You can see here, this is a sigmoid activation function which we are using in the output layer. Why are we using the sigmoid activation function? The output layer has a sigmoid activation function to output a probability between 0 and 1. So this is the code building a CNN model using the Keras library with TensorFlow as its backend. The model has different layers. Let me explain the different layers that are present one by one. Let's begin by looking at the first layer. What are we doing here? The first layer is a convolutional layer. I repeat, the first layer is a convolutional layer with 32 filters of size 3 by 3. I repeat, the first layer is a convolutional layer with 32 filters of size 3 by 3, and we are using a ReLU activation function here. The input shape is 150 by 150 by 3. I repeat, the input shape here is 150 by 150 by 3. What does this mean? This simply means that the images will be fed into the model, and these images have a size of 150 by 150 pixels and 3 color channels. I'd like to repeat the interpretation for 150 by 150 by 3. The input shape is 150 by 150 by 3, which means that images that will be fed into the model have a size of 150 by 150 pixels and 3 color channels. You can see here, to this layer, we are adding the max pooling layer. This is very, very important. Why do we need the max pooling layer? The second layer is a max pooling layer with a pool size of 2,2, which downsamples the output of the previous layer by taking the maximum value in each 2 by 2 batch. If we can understand the first 2 lines, the rest of the code would be a lot simpler. For the purpose of clarity, I'd like to reiterate what exactly we are doing here. The first layer is a convolutional layer with 32 filters. I repeat, with 32 filters of size 3 by 3. Here, we're using the ReLU activation function. The input shape in this case is 150 by 150 by 3. What does this mean when we say the input shape is 150 by 150 by 3? When we say that the input shape is 150 by 150 by 3, it means that the images that will be fed into the model, I repeat, the images that will be fed into the model have a size of 150 by 150 by 3. 3 here represents the 3 color channel, namely the RGB. Next, let's make a move on to the third and the fourth layer. The third and the fourth layer are similar to the first layer. I repeat, the third and the fourth layer are very much similar to the first and the second layer, except for the fact that we have 64 and 128 filters respectively. You can see here we are using 64 filters, and in this case, we are using 128 filters respectively. The fifth layer is again a max pooling layer with a pool size of 2,2. This is very important. The max pooling layer comes into picture here once again, and the pool size we are using here is 2,2. Let's now move on to the next layer. The next layer that we see here is the flattening layer. What does this do? This layer is a flattening layer which flattens the output of the previous layer into a one-dimensional vector. As the name itself suggests, this is a flattening layer. What role does it have? The job of the flattening layer is to flatten the output that it has received from the previous layer into a one-dimensional vector. We'll now look at the seventh layer. What is the seventh layer telling me? The seventh layer is a dense layer with 512 neurons, and the ReLU activation function is used here. The eighth layer, this is the eighth and the final layer. This is the output layer, which is a dense layer with a single neuron. You can see here, we are using one single neuron in the output. So the eighth layer is the output layer, which is a dense layer with a single neuron and a sigmoid activation function, which is used for binary classification. Overall, to summarize what we are doing in this particular code, what we are doing here is that this model uses a stack of convolutional and pooling layers. We are using a sequence of convolutional and pooling layers. Again, we are using convolutional and pooling layers. This process is repeated multiple times. Why are we using a stack of convolutional and pooling layers? Simply because we want to extract the features from the input images, followed by a fully connected layer for classification. The final layer has a sigmoid activation function, which makes it suitable for a binary classification problem. Let me go ahead and quickly execute this line of code. Let me scroll down. Here, we will be defining the model architecture. In fact, if you look at the earlier stage, we have already defined the model architecture. Here, we'll simply be compiling the model. I'll just change this. We can just compile the model. I'm using an optimizer, which is called as the Adam optimizer. When you look at the loss function that we'll be using binary cross entropy. And the metric here will be the accuracy metric. We have different options for the loss function. We also have different options for the optimizer and metrics. Let me go ahead and execute this particular code. We have compiled the model now. Now it is time for us to train the model. We will be running the function model.fit. The model.fit will be applied on train underscore generator. You can also see here epochs I'm specifying as 100. This will mean that we'll be running the model approximately 100 iteration. I have tried and experimented with 50, 60, and 70. It did not converge, and therefore I've specified the number of epochs as 100. Let me go ahead and execute this particular code. You can follow what is happening in each epoch. Right now, we are in the first epoch. Please have a look at the overall loss as well as the accuracy. You can see here, this represents what is the validation loss. The validation loss value is 0.88. The validation accuracy is 0.5. In epoch 2, the validation loss has increased from 0.88 to 1.03. The validation accuracy has remained at 0.5. You can see here, in each stage, the attempt is to reduce the loss value and to improve the overall accuracy of the model. You can see here, it is still in the 27th iteration. We are still in the 27th iteration. In the 29th iteration, we see some improvement in the validation accuracy. You can see here, the accuracy is 0.833. You can see here, after 100 epochs, the final validation accuracy that we are getting is 0.5, which is not a very high number. I would have been very, very happy had the validation accuracy been in excess of 80%. This is a very poor model that we have built, wherein the validation accuracy that we are getting is merely 0.5. The validation loss has come down to 5.47. Now, how do we improve the final accuracy of the model? There are different techniques to do it. Either we can experiment with an alternative modeling technique, or we need to get into hyperparameter tuning. I will be doing the hyperparameter tuning in a separate video, but the purpose of this video was not to build a very, very highly accurate model. The purpose of this video was to demonstrate how to use a CNN model to build a classification scheme. Let me run the last code here. Let me change the description here. In this case, what we are doing is we are evaluating the overall model performance. Let me go ahead and execute this particular code. You can see here, the test accuracy is very, very low. It is merely 0.5. This is a model which we cannot implement in a real world scenario, because unless the accuracy level is in excess of 70%, it is better to take the model results with a pinch of salt. So in this video, what we have seen is how to build a CNN model to classify a binary classification problem. With this, I have come to the end of today's video. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.